Maribel Live, where it's all about you guys tweeting me your questions for a chance to get them answered on the next live show. So if you are here, please let it be known in the chat. Say hello. I want to say hi to you guys. So I see Daniel Small saying first. Yes, you were first. Congratulations. I have another one. Tanisha saying I'm having trouble with naming Bronston acids and bases. And just want to let you guys know what we will be covering today. So I actually get questions ahead of time. I see Ryan, I see Priscilla, I see Krista Joy. Hey guys, welcome. So happy that you guys are here. I see a lot of regulars. So happy you guys are here. So I basically want to let you guys know, if you're new to this, if you're new to my Sunday lives, I always get the questions ahead of time from Twitter. So this is already the questions that I've been getting throughout the week. So I already have made the lesson plan for that. So today what we will be covering is going to be more of effective nuclear charges, atomic radii, ionization energy, finding pH, Ka, Kb, and the 5% rule. So all of this is going to be what we're going to cover today. For everyone else who is asking for different things, I recommend actually tweeting me your questions. So how you can get your own lesson and how you can get them all answered beforehand is you can tweet me your question. Okay, so throughout the week, tweet me your question, and it's on the screen. You can tweet me at hello Melissa M, and then put the hashtag Ask Melissa Maribel, and I will see it. And then from there, I'll be choosing which questions I can go over, and I'm doing my absolute best to include as many questions as possible. So I highly recommend you guys take advantage of that, because a lot of people are not taking advantage of that. So whoever's asking their questions right now are actually getting them answered on the Sunday live. So really, I recommend it for those who have already gotten their lessons, or actually already gotten their questions answered. You've seen how simple it can be and how I really do create a whole lesson for you guys. So this lesson that I just created took me quite some time. So to quickly create these lessons, I had to stay up a little bit late last night, but it's all for you guys because I truly appreciate you guys and I want you to learn. So today's tutoring session or live session is honestly worth $100 worth of tutoring, but you guys are getting it for absolutely free. That is my gift to you because I want you to succeed and do well. Okay, so we're going to start off with our first topic, which is the effective nuclear charge, and we'll go into all of these different topics. Now, what I did want to mention is if you're watching this afterwards or watching the replay, I'll put a pinned comment on this video at the bottom. You'll be able to see where I put the timestamps. All that is where the time of effective nuclear charges, ionization energy, so you can instantly skip to that part. So there's that. And then another thing that I will be talking about, if you guys haven't yet downloaded my free chemistry survival guide, I highly recommend doing so. That is in the description box of this video and really every single video. So make sure to do that if you haven't already. That includes all the formulas that you will see throughout this semester for Chemistry 1 and for Chemistry 2. And not only that, at the bottom, you'll also see more additional resources that I hand selected for you guys. So something that I hand selected for you guys, towards the bottom, you'll see it's Chegg Study. So Chegg Study is something that I personally used all throughout college. My goodness, I used it for several years, helping me with my physics classes, all my math classes, basically as many chemistry classes as I possibly could get help in, since I took so many of them as a chemistry major. So what Chem Study is, it's a homework helper. So if you are really stuck on a homework question and don't understand it, it finds a way to then guide you and actually has a step-by-step solution. It's kind of like a solutions manual in a way, but it's very, very beneficial to help you understand your homework and understand chemistry or physics or any other science subjects. So I highly recommend it. All of that is in the description box below. And then just as a disclaimer, I am part of their affiliate program. All that means is if you decide to go with Chegg Study, I do get a small commission from it, and all that goes to is helping support my channel and make more videos for you guys every single week. Okay. So with all that being said, let's jump in. So effective nuclear charge, what is it? So when we're talking about the effective nuclear charge, I want you to go way back to what an atom is and what an atom is composed of. So an atom has a nucleus, right? That's like the center of our atom. And what that is composed of we have protons that are positively charged, and we have neutrally charged neutrons. So that's going to be in the center or in the nucleus. Now, surrounding the nucleus are all of our electrons. So we're going to have something known as core electrons. All that is, core electrons are the electrons that are inside. So they're the inner electrons. And then the outermost electrons are known as our valence electrons. Okay, so we'll see that, and what we're essentially talking about, and I'll give you more visuals in a second, but what we're essentially talking about is we're kind of looking at like one electron, and we're seeing what pull is happening. So what's essentially happening like through the eyes of that just one electron. So remember, electrons are negatively charged. So since electrons are negatively charged and the nucleus has protons, which are positively charged, there's going to be an attraction there. So essentially what's happening is let's say we have these electrons here, right? This is our nucleus. And there's going to be some sort of pull to that nucleus, and it's getting stronger and stronger, but we have other electrons surrounding that electron that we were talking about before, and they're repelling. So remember, opposite charges attract one another, but the same charges repel. So they don't want to be near each other. All right, so that's essentially the concept that we're going to be going over today, and that's what effective nuclear charge is. It is, and we have this already set up, so it is the net charge of an electron, and basically what that electron experiences, meaning that electron is being pulled by the nucleus and repelled by electrons all at the same time. So I'll give you an example of that in a visual diagram just so we can see this better. So let's say this is a chlorine. This is a chlorine atom. And essentially what we have here, and I didn't put the neutrons, but I really just care about the protons for right now. And how I knew there are 17 protons, remember that the proton count is the same exact thing as the atomic number. So our atomic number will tell us how many protons there are within that atom. Same goes for electrons, okay? So we have 17 protons and 17 electrons because it is a neutral atom. So neutral atom just meaning there's no charge. Okay, so all this being said, let's say if we were looking at this electron, okay? So this is positively charged, our protons. So this is being pulled inside, okay? So that's being pulled. But what's essentially happening is all of these electrons that are surrounding this one electron, it's now repelling that. So they want to go away from each other. So there's so much going on that we can't really see, or we don't even think about, that this electron is being pulled, but it's being repelled by other electrons. And the Z effective, or the effective nuclear charge, is described by this formula, where Z effective is essentially talking about the effective nuclear charge, and Z is the number of protons. So in our case, Z would be, let me choose blue, 17. Okay. And then minus S, S is going to be your inner electrons. Okay. So the inner electrons, and those are the ones that we see here in like this reddish orange color. All right. So we have 1, 2, 3, 4, 5, 6, 7. And then, actually, I think I counted that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Cool. It should have been 10. So we have 10 overall. So I'm going to subtract that. And then this is going to give me a positive 7. So that's how I can easily determine what my effective nuclear charge is, just by using this formula. And once again, I knew, like, the periodic table tells you everything, really. So the periodic table told me that, okay, well, I have 17 protons here because this is chlorine, and then my inner atoms here, well, I know that this has to be 10 inside. And then not only that, remember that your electrons on the outermost shells are your valence electrons. So you should already know which ones are your valence electrons, thinking way back to when we were talking about halogens. So halogens have how many valence electrons? They have 7. So that's why there are 7 valence electrons on the outermost shell. And that's how I knew that, okay, well, 7 minus 17, then the remaining inner electrons, which is S, has to be 10. And that's where I get plus 7. So we're going to see a lot more of this very soon, and we're going to find a way to incorporate the nuclear effective charge with atomic radii and ionization energy. But I want to make a little statement here where as we start to increase, as our nuclear effective charge increases, we're essentially saying that the pull, so this electron and this proton here, this pull towards the nucleus is actually increasing. Okay, so it has its overall is increasing, and that's kind of like something that I just want you to honestly think of is whenever this number is larger, that just means that this pull is greater. Okay, so that's what we're going to keep seeing, and then we'll relate it in a second. So let me keep going. Okay, so now we're going to go into the atomic radii and just seeing what the trend is and what in the world this is overall. So what I've drawn is just two different atoms side by side or kind of overlapping each other. And essentially the concept is that if we were to measure the radius of, and let me actually draw this out. So if we had like the radius here, put that there and here. So if we were to kind of put those two different atoms next to each other, and if we went to the nucleus and we kind of like measured that radius, that would essentially tell us the distance between the nucleus, or really the nuclei. So these two different nuclei. So that's what atomic radius is kind of talking about. I know it's kind of complicated with the thought process there, but this is essentially what it is. However, will you really be asked that? No. So what you're going to be asked is which one has a higher, which one has a higher atomic radii. And that's what I want you to focus on mostly, but have an idea as to what they're essentially talking about. It's just the distance between the two different nuclei that we have here as shown. Okay, so this is what I really want you to know. Where when we're talking about like periodic trends, atomic radii is one of the first ones, and how that's going to increase. So as we move kind of the opposite way, so from right to left across the period, that's going to increase. And as we start to move down the column of our periodic table, that's also going to increase. If you are kind of like not sure, if you forget anything like that, what I want you to think of is this corner. This bottom corner is going to be like the highest, or actually, yeah, the highest in atomic radii. That's going to be the easiest way to remember it. So just this little corner here is going to be like the highest in atomic radii. Okay, so make sure to know this part. Now I'm going to have us kind of go into more of the concept again. I'm going to relate this now to the nuclear, effective nuclear charge overall. Okay, so now, for our effective nuclear charge, let me go back. Okay, so as we move from left to right, our effective nuclear charge is increasing, but that's the opposite of our atomic radii, right? So our atomic radii stated that from right to left, it's actually going to increase. But for our effective nuclear charge, it increases the opposite way. So they're opposites from each other. So our effective nuclear charge, as it increases from left to right, our atomic radii will actually decrease. So these two are opposites from each other. That's something to kind of note just in case you are asked to prove this based on the effective nuclear charge. Just know that they are opposites from each other. One increases while the other one decreases. And this goes back to the concept of the greater the nuclear charge, like we saw before, like it was +7, then the greater the pull of like towards the nucleus has on the outer electrons. So just think of it as like think of it as the atomic number. So our atomic number has more protons, right? So the greater the atomic number, like let's say it were 25, that's going to be a lot greater than, let's say, chlorine, which has an atomic number of 17. So what I'm saying by greater, I'm saying that pull is actually going to be greater, and our effective nuclear charge would then be greater as well. It would increase. So that's essentially the concept here. And then same thing, but we would have a smaller atomic radii. So just always knowing that they're opposites from each other, that's essentially what I want you to think of. And then let's say the opposite way, if we had a smaller nuclear charge, like let's say +2, then it has a lesser pull to the nucleus and has and then it would have a larger atomic radii because it's on the opposite side. So that's essentially what I want you to think of. Another way to look at it, as I was talking about, is our atomic number. As it increases, the effective nuclear charge also increases. So as we go from left to right from the periodic table, our effective nuclear charge increases as well. Okay, so that's kind of the concept. Let's do a question. So we have two different examples here, and I want to talk about this based on the trend that we saw before, where we know this is going to increase as we move down a column and going from right to left. So this is going to increase, okay? So what this is asking us to do is to determine which one has the higher or the greater or the larger atomic radii. Okay, so the larger atomic radii. Let's figure out which one has it between nitrogen and fluorine. So fluorine is over here and nitrogen is right here. So if we were to look at this based on the trend, we know that whatever is going furthest to the left is going to be greater, is going to be larger. So fluorine is all the way to this right corner, but nitrogen is a little bit further left. So nitrogen would be, just based on the trend, would be the one that we would see has a larger atomic radii. Now, if we were to go back to see what this would entail, or how we would incorporate the effective nuclear charge, well, we can just look at our we can look at our atomic radii. Hold on. Actually, we can look at our atomic numbers. So looking at our atomic numbers, this is 9 and this is 7, right? So we know that atomic radii is the opposite the trend of our effective nuclear charge. Okay, so, and I kind of want to just to simplify this. As we increase in our atomic radii, we decrease for our effective nuclear charge. So that's essentially the concept here, where as we increase in our atomic number, or really in this case, decrease, right, because that's nitrogen, then that means that, so since this is a lower atomic number, then I know that it has to have a smaller nuclear effective charge. So this is kind of like the main thing that I want you to think of. Okay, so just knowing that they are inversely proportional to each other, or opposites from each other. Okay, I'm going to keep going with the next one. So this is another one. So carbon, let's say if we're looking at carbon or GE, we're going to see that is here and here. Okay, so I'm looking at this trend now. So as we move further down, that's going to be the larger atomic radii. So that's going to be GE, right? Because that's lower. That is lower. So then it has to be GE. So that's kind of like the easier way to look at it when you're just asked which one has a larger atomic radii. But if you are asked to incorporate the effective nuclear charge, then this is what's going to help you out. Okay, just knowing that they're opposites from each other. Okay, I'm going to keep going to ionization energy. So ionization energy. Ionization energy is the energy required to remove an electron. So this one is completely opposite from the atomic radii. So, and then by the way, I just saw a question. Do you have notes on this topic? Unfortunately, I do not have notes on this topic just yet. I need to work on some more. But that's why I'm going over it now. So for our overall trends now, I want you to think of this for ionization energy. And by the way, ionization energy, same with electronegativity, and I believe electron affinity. Those are going to have the same sort of trends, where fluorine is going to be like pretty much the one to look at. That's going to be one of the higher, like this corner here is pretty much going to be one of the higher ionization energies. Okay, so if you forget the trend, just know that this end here, this corner here is higher in ionization energy. And then for atomic radii, it's highest on the opposite corner. Okay, so that's like a little trick that I personally used and teach my students all the time. Okay, so it increases as we go from left to right and up a column. Now that we know that, let's actually look at this and understand what in the world's going on. So remember when we remove an electron, then what's actually happening is our atom is then becoming more positive. Think of it this way. Whenever you remove something negative from your life, which is an electron, right, that's negatively charged, then you become more positive. That's essentially the same exact concept here, where this first part, this is going to be known as IE1. IE just stands for ionization energy, and this is going to be our first ionization energy. So our first ionization energy just means that we are taking, this is like the first electron that we are removing. And then let's say if we wanted to continue to our second ionization energy, that's our second electron that we are removing. So we can't do this like simultaneously. Like if we wanted to instantly go and remove an electron, like let's say 5 electrons at a time, that does not work. We cannot do that. All right, so we could only remove electrons one at a time. That's why we're going to see so many different ionization energies. Like let's say, you know, some of ours could even have like 3 different ionization energies, but we have to do this process one at a time, removing 1 electron at a time. Okay, so this first one, if I were to start off with, let's say, sodium in its gas form, and I wanted to remove an electron. Remember, when we remove an electron, it becomes positively charged or becomes more positive. So this just is accounting for that removal of an electron and that it's now positive. And plus, the fact that I removed an electron, that's why it's on the product side, because it started off as just a neutral gas atom or particle, and then it then kind of like separated apart to be charged, and we removed or took out that electron, and that's why we're accounting for that on the product side. And we're going to do that same process again. So now we're going to take our new Na with a positive charge, and then we're going to go from there and remove another electron. So then that's why we have a 2+ charge now. And we show once again we removed an electron. So this is going to be very important to understanding how to write everything for ionization energy. That's essentially just what I want you to think of. Your electrons are always going to be on your product side. Then we know it has to be positive charge. Since we're removing something negative, we become more positive. And then the next thing that I also want to hint at, or just really let you know, just in case you see this on your exam, if you were asked where on the periodic table do we see our highest ionization energy, that's actually going to be the noble gases. So your noble gases will be the highest in ionization energies. The reason for that is this goes back to the octet rule, or how many valence electrons there are overall for noble gases. And remember that those have 8 valence electrons, meaning they're the most stable. So they're the happiest per se. Okay, so since they are the most stable, they're going to have a very high effective nuclear charge. Okay, and then that's essentially the concept. Because they're so stable, it takes a lot of energy to remove an electron. So ionization energy, remember, is the energy required to remove an electron. Since noble gases are so stable and don't want to be bothered with, it's going to take a lot of energy to be able to just take out even 1 electron. So that's essentially the concept with this. Now I'm going to keep going, and effective nuclear charge with ionization energy, those are actually going to be increasing both at the same time. So if we increase our effective nuclear charge, we're then going to increase our ionization energy. So those two go hand in hand. That's going to be a lot easier to just remember. And the reason for this is because they both have the same trend. So our effective nuclear charge, I don't know why I keep wanting to say it in that order. Our effective nuclear charge is going to increase as we move from left to right, and same goes for ionization energy that we saw before. Okay. So now that we handled all of this conceptual things, let's actually do an example. So in this case, let's figure out which one has the highest ionization energy based on our trend. So I'm going to draw the trend again, and we know that now it's going to be from left to right, it's increasing. And as we move up, so increasing. Okay. So if we were to look at, let's say, aluminum versus sulfur, aluminum is here and sulfur is here. So whichever one is farthest to the right is going to be higher in ionization energy. So it's not going to be aluminum, it has to be sulfur. And that's how we would instantly define it. So then now if I were to look at another one like nitrogen and silicon, nitrogen is right here and silicon is over here. So these aren't too far apart from each other. Now, if we were to look at, let's say, like the deciding factor and you weren't sure, well, this is still kind of closest to this end or it's higher up, you don't really know which one to focus on, look at the one that's higher up. So silicon is a little bit further down, but nitrogen is a little bit further up. So in this case, we know that nitrogen is actually going to be the highest in ionization energy in this case because it is higher up. So that's something to kind of like, if you're looking at it and you're like, I don't know which one to choose, it's going to most likely be the one that is highest on top, with the exception of, and I do want to mention this, with the exception of oxygen and chlorine. So if we were to look at oxygen and chlorine, then that one is actually kind of impossible to figure out. So some people may argue that, oh, it might be oxygen, oh, it might be chlorine, but they would need to give you more information, meaning they'd have to give you a table or they'd actually have to, show you what the ionization energies are and you compare it from that. But that is a trick question. So it would be neither. You're not given enough information to be able to determine just looking at the periodic table whenever we have like oxygen and chlorine. Okay, so just in case you're looking at that. Okay, so let's move on. So all of that was talking about ionization energy, atomic radii, and how it's all kind of mixed together with the effective nuclear charge. Now we're going to kind of shift gears now and go more into general chemistry too, or if you're in AP chemistry, you will most likely see a little bit of this as well. So what I'm going to be going over is the first part here. So finding the pH of some sort of solution, and we're given our Ka value. So essentially what we're doing is we're finding the pH of a weak acid. How I personally instantly know that it's a weak acid. So let's kind of go back to what a weak acid is. So remember that a weak acid will not completely dissociate, and dissociation just means separate or break apart into ions. So because this is so bulky, and since this solution is so large, right? We have so many so many carbons, hydrogens, oxygens, and there's another hydrogen that's H2. Because of all of this, I can see, well, that's not going to be able to dissociate quickly, right? It's too bulky. Something like HCl will be able to dissociate really quickly, and that's going to be a strong acid. Another little hint is the fact that it has a Ka. So our strong acids really don't have a Ka. However, our weak acids do. So that's another way that I instantly know that, okay, this has to be a weak acid. All right. So let's start off with just finding what our pH would be in this sense. And where we always want to begin is with our balanced equation. So that's exactly what we're going to start off with. Now, it didn't really give you enough information, right? So it doesn't tell you, oh, what do I have to combine this with? So because we're just instantly given that this is a weak acid, well, what are we trying to do? We're trying to make it dissociate or at least partially break apart, right? So since we're trying to partially break this apart, then I know I have to put this in water. So that's always going to be the case with these types of questions. So if you don't know where to start, make sure to start with the balanced equation and adding this just to water and seeing what that effect is going to be, okay? So the next thing is, how do you predict the products? It's actually not as bad as it seems. So since we already know that this is our acid and this is our base, because this already started off as an acid, right? This told me it's a weak acid. Then water can act as either an acid or a base. It's something known as being amphiteric. So that's what I want you to essentially think about. Okay, so let me show that. This would have been our acid, our weak acid. This would have been our base. This goes back to, and actually someone had a question on this. This goes back to our, what was it called? Bronsted-Lowry, acids and bases, okay? So the fact that we have an acid, remember that an acid will donate a proton or donate an H+. So proton is essentially just an H+, okay? That's all I want you to think of. Now, because we're going to donate a hydrogen here, okay, and we donate this to the base, our base, the definition, is saying that we're accepting an H plus or a proton. So then I instantly know, well, then, okay, since this is going to donate, then I must see that this no longer is going to be a 2 and it's just going to be a 1, right? It's going to be on its own. But then with our base, since that's accepting a proton, so H plus, instead of a 2 here, it's going to go up to a 3. And it becomes positively charged because a proton is positively charged. So since we added an H plus, then that means we're going to end up we went from something that is neutral to something that does have a +1 charge. So I hope this is making some sense. This is how we're actually going to figure out all of our different equilibrium reactions, and I'll go over every single one just so you know how to be able to just instantly tell what this is. Okay, so now that we have that and everything is balanced, luckily, I'm going to start off, and let me actually look back at any questions that you guys may have before I move on. Melva's saying, I had a test where we had to find the pH, but was unable to use the calculator. Is there a way to find the exponents without a calculator? Yes. So they would have to give you, and I'll see if I can do it with this example. But they would have to give you like easier numbers. Like they'd most likely give you like 1.0 times 10 to something, and then you'd be able to figure it out. So I'll see what I can do within this question or another question. And then I'll look more down and see, since we're on a different topic. Ryan's had a question on, I'm confused with the whole proton being hydrogen thing. Does this mean that all elements have a positive charge, have hydrogen? No. So whenever we're just talking about, this is kind of a little bit different here. We're sure everything has protons in it, right? So that's just talking about what an atom is and what's hidden inside of the nucleus per se. And actually, does everything have a hydrogen kind of hidden within it? Technically, yes, because that's what a proton essentially is. So in the very beginning, you guys don't get into what a proton really is. You just kind of get this vague explanation of, it's some sort of subatomic particle, just meaning it's really tiny. It's a really tiny particle that is positively charged. And then now, as you kind of go a little bit further into chemistry, we're going to build on that idea and state that, yes, H plus is our proton. That's how we define it as an element, or as, kind of more in-depth explanation of what a proton is. So technically, yes, all elements can have an H plus in it. That is essentially what we're talking about with a proton. But I just want you to think of, for these types of explanations, that especially acids and bases, whenever we're talking about donating a proton or accepting a proton, we're just saying like, we're just giving away an H plus, or accepting, or receiving an H plus. So that's the concept here. Okay, so with like an actual nucleus, don't worry too much about the fact that, is a proton H plus. Don't worry about that because you don't really focus on that. But here in acids and bases, we do. I hope that makes more sense, Ryan. So I'm going to keep going with this question. And the first thing we want to do with this types of question is the fact that we don't have much information, right? We have our Ka, we have our some sort of molarity that was given for our weak acid, but we have no idea what our products make, right? We have no idea what our products make, and we don't know what this is at equilibrium. So a quick little thing that I want to mention. What is equilibrium? So equilibrium is essentially saying where our reaction is balanced, okay? So it's kind of like just saying it's the chemical way or chemistry way of saying we're balanced, right? So that's essentially kind of what I want you to think of. Another cool thing to think of it as, it's like a roller coaster where you're kind of, I personally don't like roller coasters, but when you're kind of going up and then you go down, you get this like uneasy feeling, at least myself, or to other people, a rush, where your body is no longer at equilibrium. That's why you kind of feel like how do I explain it? Kind of like that. You kind of feel like higher than life or something like that. Like you just feel different, right? I think you guys all have been on a roller coaster, so you know what I'm saying. And then once you kind of get down and get back down to just how you normally feel, that's kind of like equilibrium in a sense, where your body is going back to its normal state. So that's what I want you to think of with chemistry. The reaction is kind of leveling out and going back to that balanced. Okay, so that's essentially saying what's happening. It's also saying that after the reaction has already happened, after we've created our products, then it's leveled down and gone to just be balanced. So that's how I kind of want you to think of it, if that visual helps you with it. So let's keep going with this. What we want to do is build something called an ice table. So what an ice table is, and what it's essentially telling us, is I is going to stand for the initial amount or initial concentration. So everything that we're using in an ice table has to be in molarity. So, and that's just what concentration is measured in. And that's why we're given everything in molarity already. So everything here is going to just be our initial value. We initially know that we're given 0.1 molarity for our weak acid. And then water, by the way, is irrelevant. The reason why water, we don't care about it, is because it's in its liquid form. For these types of questions, we only care about things that are in their aqueous form, actually. That's what we're going to focus on. Everything in their aqueous form, nothing in a solid form or liquid form. We don't care about that, okay? So that we instantly kind of say, nope, that's out. I'm not focusing on that, all right? And then next, we don't know what our products are actually going to produce, because initially they're not there, right? So initially the only thing that will exist is going to be our reactants. But at the E part, or equilibrium step, that's where our products come to life because we created them. And then next, our change is going to be something known as like minus X. So your reactants are always going to be, you're always going to subtract your reactants, so minus something. And then your products are always going to be plus. The reason for this is because reactants are being used up while products are being produced. So from here, the reason why I chose this was just really a 1x is because there's no coefficient in front. And if there were a coefficient in front, let's say if this was like a 2, then if this were a 2, then I would have placed a 2 in front there. All right, so it does depend on whatever coefficients we initially have. But in this case, we don't have that. So then I'm going to keep going. I know my products are plus X and plus X. All right. So then the next step with our equilibrium phase is just adding these two together. So we're going to combine these two, combine, and that's what our E part is. It's just our equilibrium step. All right. So we combine those two together. This one is X and X. And the next step is to write our Ka. And I want us to understand what that setup is going to look like. So for our Ka, essentially what this is saying is we're going to have our products, concentration of our products on top, and then our reactants on the bottom. If we were to have, let's say, a coefficient of 2 there, that coefficient would have been our new exponent for that specific product. But in this case, once again, we do not have any value that is greater than 1. All right, so we want to build this, and that's exactly what I'm going to do here. So here you'll see that this was our product, right? That was our first product. That's why I placed it on top, times our second product. That's also on top. I don't care about the water. That never goes in our equilibrium constant, or in this case, our acid constant, so ionization constant. So this has to be on the bottom. So once again, products on top and reactants on the bottom. So that's how I knew that this is Ka. All right, making sense so far. Let me know if it's not. So this is what I'm focused on, and what I can do now is plug everything in. So because I know that I'm just looking at everything at equilibrium, and that's what Ka has to be, by the way, when we're figuring this out, we want to know those equilibrium values. So that's why I even use this ice table to be able to figure out what this equilibrium value can possibly be. So our X here comes from these two X's on our products, and I just plug those in. So I plugged in an X here, and I plugged in an X here, and that's how I got X squared. And then same thing for this bottom part, I ended up just using the equilibrium portion of our weak acid, or, our first reactant, and I placed that at the bottom. All right, so I'm going to keep going with more space. And we already were given our Ka value, so I'm just going to plug that in, and then I'm going to solve for X. Okay, so plug that in. All I have to do now is essentially solve for X. And I'm going to actually go over, I'm going to go over the 5% rule. So 5% rule, also referred to as the X is small assumption. Those go hand in hand. So essentially what this is saying, the 5% rule, is it's talking about how we can just kind of say, oh, like I just canceled out that X on the bottom. I can essentially state that X is kind of irrelevant, where it won't change my initial value. So it won't change my initial concentration that I was given because it's so small. That's why its X is small. So if we were to assume that, I would cancel out that X on the bottom, not the one on top. It's only the X's that are being subtracted or added that we can cancel. And then I would solve for X overall. And remember how I would do that is I'd multiply both sides by 0.100. After I get that value, this is X squared, and whatever that value would have been, running out of room, I would have then taken the square root of both sides. All right, so that's essentially the concept. And then I get X. I get this as my X value. Okay, so next, the 5% rule is essentially saying this. It's whatever that X value that we just found, which is this first top part, that's going to go on top. And then on the bottom, it's going to incorporate our initial concentration of our acid. So our initial concentration of our acid was this 0.100. All right, so 0.100 would go on the bottom. So that's exactly what I'm going to plug in. I'm going to multiply this by 100. And then from there, I would have gotten 2.8%. And what that's telling me, whenever we are checking the 5% rule and we're seeing that, oh, it's below 5, then I know that that must be correct. That must be valid. And we're allowed to cancel out that X. So yes, it's valid. Another thing, a little trick that I like to tell you guys is if we were to just look at Ka, we can instantly see if the X is small assumption would work. And the reason we can do that is because if this is either -5, -6, and so on, -7, -8, all right, so if we have any of that, then that's going to mean that, yes, X is small. But if we had 10 to the power of -4 or 10 to the power of -3, -2, and so on, then no, we have to double check if the X is small or the 5% rule that I just showed before. All right, so that's going to be a quicker way to just instantly tell what to do there. Now, for those of you saying or thinking, what if it's not valid? What if the 5% rule doesn't work? What do I have to do? Well, that means I can't just decide that this X is gone. I then have to leave it and use the quadratic formula. So it's just a little bit more work, unfortunately, but it's still doable. You would just use the quadratic formula to solve for the X value, and that's going back to algebra. All right, so that's essentially the concept there. I'm going to stop real quick and just go on to questions. I see a question from Melva. Is there a way to calculate for Ka if given the milliliters and density alone? With the Ka, I may have worded wrong, but I know that density was given. If density were given, so density would have been grams per milliliter, right? So just the density alone. Yes. So here, I see what you're asking. Yeah, so if it were grams per milliliter and the density, I'm just thinking of the question I can possibly throw. If this were, let's say if this were 0.1 grams per milliliter of, I'm going to think of a weak acid, HF. So moles, grams, yes. So what I'm going to do is I would have used the molar mass of HF. And the reason why I'm doing that is because that would cancel out the grams and I would get moles on top. And essentially what I would want to do is I'd want to change this to molarity. And remember, molarity is moles divided by liters. So I would find my way to actually do that. And then I would actually have it already. Like I would pretty much have my ice table set up. So if that makes sense, my first step would have been to change the grams per volume to moles per volume, and that would give me molarity. So I just do that by the molar mass of whatever acid they provided, and they have to provide an acid or else the question isn't doable. All right, so that's what you can do, Melva, in the case that they gave you density. Change it to moles over liters, and then that will start off with that would then give you, let me see if I can go back. That would then give you something like this. And then once again, you'd have to write your balanced equation, just whatever acid you're given, add it to water and figure out your products, build an ice table now that you have the initial concentration. This is 0, 0, and so on, and you'll be able to get your Ka value. They have to provide you with something else, like let's say pH, or I'm trying to think what else, or the change overall that's happening, but that's what I can think of with the question, since I'm not given a question, so I don't know just yet, but that's how I can think of it instantly right now, which is density. Yeah. All right, let me go back, guys. And actually, even before going back there, so what we just talked about was the 5% rule, right? And we stated that it was valid. Now, since x is small, and we found what x was, the reason why we're solving for x is because we're asked to find the pH, right? We're asked to find the pH. Remember that our pH formula is really just dependent on the concentration of our acid, all right? So the concentration of our acid is x, right? That's exactly what we saw right here. H3O plus is the acid. So that's hydronium. All it's talking about is how much acid we essentially have left over, okay? So that's why we care about what x is. And so I did all of this, and we figured out what our x value is. Okay. So then now what I'm going to be, thank you, Ryan. I appreciate that. So Ryan just said Melissa Maribel is the best chemistry tutor. Thank you. Really, I really appreciate that, guys. I try my best. So if I were to solve, so we just solved for x, right? So we just solved for x, and I'm going to pretty much go back and replace this with all of the x's that we had previously on our initial ice table. And if I were to do that, then this is what it would look like. And I now know the concentration of my hydronium or my acid concentration. And this is kind of like the formula that you'll see. By the way, what you could have also seen here is this could have been written as hydronium as well. And those mean the exact same thing. So like H plus or H3O plus, those are the same thing. It's still just talking about the acid concentration. So then that's why, since we're looking for pH, that's why it was so important to know what that X was, because all I have to do is plug it in now. So after I plug this into my calculator, then I'd figure out that my pH is 2.55. And then that essentially would be the answer for that first question. All right, so that kind of went over pH and everything else. And then let me see if I have time for another. Yes, let's do this one. So let's say if we wanted to find the Ka now. So this one's a little bit different. They give us some sort of concentration of our weak acid again, and they also give us our pH of 2.75, and we're asked to find what the Ka value is this time. So first things first, build your formula. So build that balanced equation. And then I instantly know I have to combine this with water since it has to dissociate or just break apart, right? It's going to dissolve. So I have this, and what's going to happen? Well, if this is my acid and this is my base, then I have to donate a hydrogen here, right? Because that base is going to accept. So since that base is going to accept, that's why we see, oh, we lost a hydrogen here, right? That top one or that front one. We lost that, and then we gained the hydrogen on our base, and that forms that hydronium ion or acid. So now what I'm going to do is I'm going to start building that ice table, and we're given our initial concentration of our weak acid. So building the ice table, we have this already. That's what we were given. We don't care about water. That's irrelevant. Since that is in its liquid state, we don't focus on that. We only look at everything that's in its aqueous state. And then this is also 0. Next, I'm going to include the change. So our reactants are always minus, our products are always plus. And then next, I'm going to combine these two values together. So I'm just adding these two, adding and adding. And that's what we get first for our equilibrium. And the next ones. Okay, so I really put everything into the Ka sort of setup, and just going back to what Ka was. Remember, it was our products, right? So both of these products being multiplied and their concentrations. Brackets just mean concentration. What does concentration mean? Molarity. So now I also have my reactants on the bottom. All right, so that's how I do it. Just products over reactants, and that's it. Next, I'm going to plug everything in. So we know what our concentration for our hydronium ion is. It's just X. So I would have put an X here. So I'd put an X here. We know what our concentration for the conjugate base would be. So this would also be an X. And then next, we knew what this value was. And that's exactly why I got this. So we got X times X, so X squared, and the bottom value. All right, next step is, since we're given our pH, and let me get to that. Perfect. Since we're given our pH, we're going to actually figure out what X is. And the reason we can do that is, remember that we said that our X value tells us the concentration of our hydronium ion. But if we're given the pH, we can work backwards from the pH and we can actually get to what the hydronium ion or acid concentration was. All right. So that's exactly what we're gonna do, and I'm gonna show you how to do that. So this is the formula that we would use, and then remember, as I mentioned, that H plus or this hydronium ion is the same exact thing as H plus. So we're going to have the same exact formula where we can just put 10 to the negative some sort of pH. And in this case, this is the pH that we were initially given. That's exactly what I'm going to do. And in my calculator, I would put second log and then put the negative pH value. And that would give me my answer. So don't put, don't actually write 10 and then try to raise it. Use second log on your calculator, just in case you see that. So next, let's see. I'm actually given a concentration. So after I do this in my calculator, this is what I'm given. This is my hydronium ion. And I'm going to replace this back because this is what X is essentially equal to. That's what we found before. Then all I have to do is replace X and plug it in. And that's what I did. We'll do this math, and then we're done. We get 1.4 times 10 to the negative fourth. So this one isn't, I'd say, as bad, since we instantly kind of can figure out what our X value is. It's just pretty much knowing how to use or how to look at the question. And I think a lot of students, where they go wrong, let's see if I can go back, where they go wrong is this first initial step, where you're given all this information and you're like, do I use an ice table? What do I do? I'm not sure what to do. And I highly recommend to always write the balance equation. And if you're asked to find the pH and you don't have enough information, right? pH, we have to know the acid concentration. So no, we're not given enough information. We have to build an ice table. And then same goes for this other concept, this other idea where, we have to find the Ka. Well, if I'm looking for the actual Ka value, not just the expression is this, and then our Ka value is an actual number, then I know I have to build an ice table because this is just the initial, or the I portion of the ice table, rather than the equilibrium. So that's kind of telling you when you need to know when to use an actual ice table when you're not given enough information to solve what the question is actually looking for. So that's my hint to you. So always start off with actually writing the balanced equation, because that will help you out a lot. I'm going to do one more question, and this is now going to be finding the Kb. All right, so finding the Kb. We're once again given the pH of our solution of ammonia, and we're given our concentration, and our pH is 11.612, and we're asked to find the Kb. It's a tiny bit different here. So we're not going to find the acid concentration. Instead, we care about the base concentration, which is OH minus. So I really started this off where I'm still going to use this as a base, right? And then I'm going to add this to water. But in this case, since this is our base and water is now acting as our acid will donate a hydrogen, right? So one of these hydrogens is going to donate. And that's why we gained a hydrogen on that NH4, and it's positively charged. And we lost a hydrogen here on the opposite side because it's OH minus now. And whenever you lose someone positive, you become more negative. I hope not. But that's essentially the concept here. When you lose an H plus, you become more negative, and that's why we have a negative charge. Okay. So that's how I'm just figuring out how to do this already. Next, I'm going to start writing everything out. So we're given our initial concentration was this amount for ammonia, and that's what I placed. We don't care about water. We're not going to know what our products have already produced. And then our change is still the same. minus on the reactant side, positive or plus on the product side since we're producing them, and we're just adding straight down. So let's go back. All right, so then I really set up everything for our KB. Here we go. So everything for our KB, same thing applies. We're still going to look at our products, and that's what's going to go on top. And we're going to just focus on our one reactant, not on water since it's a liquid. And that's going to go on bottom. Plug everything in that we already know. So we know X and X, so that must be X squared because I placed them here. And those two are being multiplied. And I really know that this is the concentration of NH3, so that must have been there. Next step is to actually figure out what our OH minus concentration is, or our base concentration. So we're given our pH. What we can do, we're going to take a couple steps here where we're going to figure out what our acid concentration is based on our formula. And actually, you know what? We're doing a different approach. That's right. I like this way better. So let's use this formula instead. The reason why I'm using this formula is because then I can figure out what our pOH value is. And then from our pOH value, then we can go backwards and get our OH concentration, which is the base concentration. Okay, so I just plug this in. I know what my pH value is. I plug that in. And all I have to do now is subtract both sides, and that's going to give me what pOH is. All right, so I know what pOH is in this case, so that's good. Now I'm going to apply this next formula. And I'm just going to place this here, and that's going to be a negative. And that's going to now give me my concentration on my base. So now that I know my concentration on my base, or essentially my X value, right? So I'm going to replace this all with X because that's exactly what I know it is now. I knew it was the X portion of this just because of that ice table that we previously found. And then from here, I'm going to replace all the X's. So all of these X's, I'm actually going to plug in, and then I'll do the math. So I'll plug in that X value. That's my KB, and I'm done. What if, one more little question, what if from this step, they asked you, what is your Ka? Don't freak out. It's actually very simple. It's another formula. So if we were asked what's the Ka, we would use this formula, okay? Where you might see it also as this. It's Ka times Kb is equal to Kw. This is the constant for water, so that's why it's W, just meaning water. Now, all we would have to do is plug it in. So plug in Kb into this formula. From there, I'm going to divide both sides. So I would divide both sides by 4.1 times 10 to the third, and the same thing on the other side. And then I get my Ka value, and I'm done. So just in case they ask you for both. So if this is like a two-step question where they say, find the Kb, then part B, find the Ka. This is the formula that you would use to solve for everything. All right, so I hope that's making some more sense now. That was going over everything with Ka, Kb, and finding the pH as well. I did also want to make a note. So all the formulas, once again, that I covered and that you see here, even in like pink and everything that I went over, those formulas are in the description box. So the download is going to be the free chemistry survival guide, and that includes chemistry 1 and 2. So if you haven't downloaded it, please do. I highly recommend it. It has all of these different formulas, constants, different tables that I personally think it is very beneficial for you to remember. So make sure to download that. And another thing I wanted to mention is at the bottom of the description box, you will also find more resources. So if you need help with homework, if you're not understanding your homework, I remember back when I was a student, I had so much homework. A lot of times I didn't understand every single question and I felt frustrated. So to help relieve with that stress or frustration, I have placed those links, something called Chegg Study. What Chegg Study does is it helps you out to understand and kind of better explain that homework question if you're struggling with it, with step-by-step explanations. And that's something that I personally use for, I use it for my physics classes, several math classes, and several of my chemistry classes since I took so many for several years. So I highly recommend checking it out if you are struggling and just kind of want to stress less. Personally, that helped me a lot. So all of those links are in the description box at the bottom. And as a disclaimer, I do want to let you know that I am part of their affiliate program. All that means is if you decide to go with Chegg Study and purchase it, then I do get a very small commission. And that just goes to helping with my channel. So helping support all the videos and props and everything that I purchase for the videos to give to you guys every single week. So that's kind of what I wanted to mention. Another little thing is if you want your questions answered, if you have other questions, you want other things that I personally, haven't talked about just yet, then please tweet me. So how this whole process is, if you're just joining me, this was your first live session, then how I changed it up this time around is that you guys tweet me your questions at, tweet me at Hello Melissa M, and then use the hashtag of Ask Melissa Maribel. And then after you do that, make sure to take a picture of your chemistry question or a chemistry topic or, whatever you need help with. And throughout the week, I will be choosing questions to go over for the following Sunday live tutoring session or live show. So that's how I decided to pick these questions already, because these are students who previously tweeted me their questions. So highly recommend it, guys, because not everybody is tweeting. So that means if you tweet, you most likely will get your question answered on the next Sunday. All right. So, and then Ryan actually just said, thank you, Melissa. Wish me luck on thermochemistry test on Friday. Good luck, Ryan. I'm sure you will do very well. And for everybody else as well who has a test coming up, keep studying, guys. Keep going. Keep moving forward. And you're already kind of midway in the semester or further in the semester, so keep pushing through. All right, guys. So I'll see you in the next Sunday, and I hope you have an awesome week and crush those exams and do great. All right, guys. I'll see you.